Uh, Good morning, everybody. Welcome to our last morning session. Our first speaker is Petja Patkinen, and he's going to talk about heavy quartz and the jet as a proof of nuclear parton from LAC, PA to gamma A collision in UPC and at EAC.
Yep.
Please go ahead.
Okay, thank you. Hope you are hearing well. First of all, thanks a lot for the invitation to come here to Sao Paulo and speak in this conference. It's a real pleasure. And sorry about the long title. I hope it will make sense in the end. So, phrasing it in other words, what I will be talking about is something that Elke introduced in her talk on Tuesday, which is the complementarity of different probes and how they can be used to test basic QCD concepts such as factorization and the universality. And in particular, I will be talking about them in the context of the nuclear PDFs and from the point of view of hard probes in PA, MA, and EA collisions, and trying to also motivate why the EIC is so important for our studies. So, since we recently heard so many talks on the saturation framework, I just thought it's good to remind of the framework in which we are working, which is, of course, the collinear factorization of QCD, where the cross-section for an inclusive final state, which involves a hard scale, can be described as a convolution of coefficient functions, which we calculate from the covariant perturbative QCD, and then the Barton distribution functions, which, on the other hand, we do not have or cannot calculate it directly, or the next speaker, I guess, will talk about how we could. And then we have these higher twist terms, which, however, are suppressed if we are working at a high enough momentum scale. And the concept that is very important to us is the universality of these PDFs. So they should be independent of the process at hand, and also their scale evolution is covered by the D-club evolutions. And now this is the framework which every PDF analysis is using and testing further. Now, for the nuclear PDFs, the concepts are the same. So they are fitted in a similar global analysis as their free proton counterparts, and we want to rely only to the QCD collinear factorization in the assumption that all the nuclear effects can be incorporated in the nuclear PDFs. And by working in this global analysis framework, this gives a model agnostic way to study the nuclear effects. Now, in this global analysis, the bulk of data are coming from large X and relatively small Q squared. But now, recently, the LHC has been extending our reach in the Q squared X plane by many orders of magnitude, particularly with the electric bosons and the die-jet and heavy quark measurements. And the EIC will, in the future, do the same for the electron-ion collisions. Now, just an example of how things are parameterized. So typically one talks about the nuclear PDFs in terms of these nuclear modification functions, which tell how the free proton PDFs are modified in the nuclear environment. And these nuclear modification functions exhibit the typical shape of a high X motion followed by the EMC effect, then anti-shadowing, and at small x the shadowing. And these effects grow in the nuclear mass approximately as a power law function. Okay, some different groups use different parameterizations and fit to different data. And here is a comparison of some recent sets. So the large X constraints from DIS and Drelian have provided for a long time good constraints on the behavior of the U and D quarks at large X. But once we go to smaller X, we are lacking the constraints to really pin down these modifications. Also, for the strange quark, we basically don't have good constraints at the moment, so they could be modified based on data by any amount we don't know. And much of the progress in recent years has been in constraining the gluon content, particularly from the LHC data. And now we are starting to really establish that there is some amount of anti-shadowing in gluon in lead nucleus, and there is shadowing in the small x region. But as you can see, there are still large variations of tens of percents between different analyses. And now I'm trying to give some description of why this happens. Okay, so this is, of course, due to the different choices made in this analysis. One important aspect is the data selection, but also some phenomenological choices like how you parameterize your function can also play a role. And as I will discuss, we have some differences in the ways how we include some data sets in the analysis. So many new analyses in the recent years, and some of them even working in next to next leading order in perturbative QCD. But these sets have quite a limited number of data included in them. And I'm going to more concentrate on the more global NLO analysis, and in particular to the dijet and heavy quark measurements in them. Now, why do we like these processes is, of course, that since they are fully QCD, they involve can involve any type of partons in the initial legs, so which includes the gluon. And so if we want to include the gluon at leading order, so these are good probes of the gluon content. Now, but this fully QCD process means that there are additional complications. So in the case of hadron production, you need to take into account the hadronization with the parton to hadron fragmentation functions, which in the context of PDF fits is a source of uncertainty. This kind of need for the fragmentation functions can be, we can get away from that by studying jet production, where now instead the complications arise from the needing a good definition of the jet that works both in theory and experiment. And then there are these non-perturbative corrections. So actually I should include here a KNP, which is needed in order to have a representative comparison between the data and the theory. So furthermore, when we study the heavy quarks, there are additional complications from the fact that this can be done in different schemes. So One very simple one is to work in the fixed flavor number scheme, where the heavy quarks are always produced at the matrix element level, such as in this vertex here. And in this framework, one includes all the mass terms, but on the other hand, then the calculation includes these logarithms of PT over mass, which come from the vertex, and which diverge when we are approaching the linear limit. Now, other option is to work in a zero mass scheme where you neglect the mass of the quark but allow them to be produced also in the initial state radiation and final state radiation, which then resums the logarithms, but as I said, ignores the mass terms. Now, one can so these have a range of validity. So the FNS is valid at small pt, where these logarithms are small, and then the zero mass scheme is valid at a large pt, where the mass terms can really be ignored. But one can combine these in these general mass variable flavor number schemes. So there is not just one of these schemes, but there are different choices how to make this. But the idea is just that you include both of these types of diagrams. But then since at collinear limit, this splitting has been included already in the partial distribution function of this, you need subtraction terms to prevent from double counting. Now, very important aspect is that this includes also the gluon to heavy flavor fragmentation, which, as was shown by Helenius and Paukkonen, gives a large contribution to the cross-section. Okay, moving to comparison with data. So LHC-B had a very nice measurement of the D0 production at LHC, both in forward rapidity, where one bin is shown here, and in the backward direction. And as you can see, when these data are included in a nuclear PDF analysis, the uncertainty shrinks quite dramatically. So comparing here the earlier EPPS 16 resulting gray band, and now including this data in the EPPS 21, we have much smaller uncertainties. And this gives important constraints for the nuclear gluons, as has been discussed in many papers already. These data were included also in the NNN PDF 3.0. However, whereas we used this general mass variable flavor number scheme in the EPPS analysis, they instead work with a Pauheg plus Pythia approach, which is like this fixed flavor number scheme, but then folded with Parton shower. So it's not a full general mass scheme in that sense. So there really the heavy flavor is always produced at the matrix element level. Now, what they found was that in this calculation, there is a large scale uncertainty shown in orange band here. And due to this fact, they only fit the forward data, which gives a large reduction in their uncertainties as well. However, we do not see similar large scale uncertainty in the general mass scheme that we use. And we were able to include all the data. On the other hand, there are some differences in the cuts placed. So we use a cut at the PT3, so include only the high PT cross sections, because there are still theoretical uncertainties in the very small PT region, whereas NNPDF used the data all the way from the zero. So these kind of choices in the data selection can cause some differences in the results. Now the NCTEC 15 HQ used yet another approach in incorporating the heavy quark data in their fit, using this data-driven approach, which was invented by Landsberg and Shaw, where the idea is basically to fit the matrix elements, not calculate them from perturbative QCD, but fit them with the proton-proton data. Of course, you need to make some assumptions, so they use just 2-to-2 kinematics and work in the assumption that only the gluon-gluon initial state is needed here. So using their parameterization, they fit the proton-proton data and then use these fitted matrix elements to fit the nuclear PDFs with the proton-led data. And they get a very nice fit, and the data constrains the heavy quark, the gluon distribution in lead in their analysis. But maybe I jump a little bit back to this slide. As you can see, this leads to somewhat different results. And this should be taken into account when we compare to new data, such as the new 8 TeV measurement from LHCb, which has not been included in the NPDF analysis yet, where in the paper, the LHCb compares only to predictions from the HELAC matrix element fitting results. And so these still need to be scrutinized with direct QCD calculations. Now, let's move to jets. And we have from CMS this very nice data at 5 TeV, where they measure this double ratio of self-normalized proton-lead rapidity distribution, and the same for the proton-proton, and take the ratio of these. Now, this is convenient for the reason that we expect cancellation of the hadronization and luminosity uncertainties separately here in the proton-lead normalization and in proton-proton normalization. And so we do not expect strong non-perturbative effects, and thus they are not included in the calculation. Now, and then when you take the ratio of these two spectra, you have cancellation of the free proton PDF and scale uncertainties. And thus one gets direct access to the nuclear modifications. And when you calculate this process at next to leading order PQCD, you see you get a very good resolution to the gluon nuclear modifications in a wide range of X. So these data have been also included in both EPPS 21 and in NNPDF 3.0. And again, in this large rapidity window, they provide very good constraints on the NPDFs, as can again see in the shrinking of the uncertainty band. Now both our analysis and the NNPDF find difficulty in fitting the most forward data point. And we haven't been able to figure out what causes this. It's like every data point in this rapidity bin in different bins of PT. So it seems that it's not just statistical fluctuations, but still we don't know what is the origin. And what complicates this is actually the self-normalization. So these very nice peaks in X, once you self-normalize, this has or changes how a single bin probes different X's because then in the normalization you have a contribution from every other rapidity pin. So, and also we don't have access to the data correlations. They were not published, so hard to say where this comes from. And maybe it's an NLO effect or some non-perturbative effect that would be larger than what we suspect. But altogether, new data from the same process or some complementary data would be very helpful. And indeed, photo production in UPCs has been promoted as a nice environment to study the nuclear PDFs. And as has been mentioned already, so in these processes, the two nuclei are passing with a large impact parameter, and so there is suppression of the hadronic interactions. But on the other hand, you can treat the photonuclear processes in equivalent photon approximation, which gives a very nice and clean probe of the target nucleus. And well, to me, this reminds of Afro-Brazilian game of capoeira, where the two players are interacting with each other without actually touching. And the processes in these UPCs that have been promoted for NPDF studies are, for example, the exclusive shape site production, where there has been in recent years good progress in calculating these processes at next to leading order precision. And there was last year first study where these NLO corrections were applied in the context of UPC lead-lead. Now, these are exclusive processes, so one cannot just use the traditional PDFs directly, but in the region of small skewness, it is possible to connect these through Shuvaev transform. Still, what was found in this study is that this process actually suffers at next to leading order still from a very large scale uncertainty. So this makes one question about the perturbative convergence of this process. But if you're interested in that, there is some work by Flett et al. To try to resolve this in a so-called Q0 subtraction. Also, what was found was that actually the quark contribution to this process is quite large. So at the leading order, you have only gluons, but at next to leading order, the quarks start to contribute and make a big difference in the cross-section. So there are still theoretical complications in using this as a probe of PDFs. And maybe a more clean process is to use inclusive die-jet photo production in the UPCs. This process happens either through direct process where the photon from the source nucleus interacts directly in the matrix element, or through resolved processes where the photon fluctuates into a hadronic state, and then we have the QCD interaction there. Now, last year, Atlas showed their preliminary results for this process, but now they have been fully unfolded for the detector effect. So we are expecting a final data pretty soon. So it's interesting to study this process. And the measurement is even triple differential, so we can really study the QCD process and the nuclear properties in this process. Now, the previous NLO predictions by Gouset and Claassen have been performed in a point-like approximation of the photon flux from the source nucleus. And one could ask, could we actually do better, or should we? And this is something that I have been studying recently. And so this is still a work in progress, but I think the results are interesting and relevant also for this meeting. So let's assume this kind of impact parameter dependent factorization as was studied by Greiner et al. Already some years ago. So in this picture, the two nuclei are separated by this impact parameter B. But then this is not the same vector as where the flux or where the hard process is actually happening. So, because it can be anywhere within this nucleus B as is described by this vector S. So then the R describes the distance from the source, center of the source nucleus and enters in the photon flux. So the things that are involved are the photon flux, then the Barton distribution within the photon, then the Barton distribution within the nucleus at some distance S from the center, and then we need to take into account the UPC condition that we don't have a hadronic interaction between the two nuclei. And why is this relevant? So if we have a large distance between the two nuclei and thus we are having the hard interaction far away from the source nucleus, then the nucleus B can assume any configuration within this transverse plane. So every point of the nucleus will be sampled equally. And this is kind of a Chokuchi fora in capoeira, where the two players can do any acrobatics they like because they are far away and will not touch whatever they do. But then if you bring the players closer to each other, you enter this Chokuchi dentru, where you have to be more careful or you might get hurt, believe me. So the same applies for the nuclear collisions. So if we are taking a collision where the hard interaction happens closer to the source nucleus, now some of the configurations of the nucleus B will lead to UPC cross sections, but then other hadronic interaction will occur. So this doesn't fulfill our requirement for the UPC measurement. And so, well, let's get more quantitative. So first, let's assume that we can factorize this special dependence of the nuclear PDFs in this way that you have just the nuclear thickness function multiplying the traditional nuclear PDFs. And then one can actually write this cross-section in pretty usual terms with a effective photon flux, which is then convoluted with the hard process and the traditional nuclear PDFs, where this effective photon flux can be given in this form, as was actually done by the Atlas collaboration when they reweighed their Pythia predictions in describing the data. So let's start with the very simple approximation, which is the point like 1. And now, so you take for the nuclear thickness function just a delta function. You don't care about the spatial distribution there. And for this gamma AB, which tells you which is the requirement of a UPC process, here you just take that you have to be at impact parameter larger than some a minimum value, which is taken to be the 2 times the radius of the nuclei, and in this case 14 Fermi. And so the point-like photon flux is quite simple. It's given in here, and if you use these approximations, then you just can do all the integrations analytically, and the photon flux is this well-known form where, depending on the beaming parameter. So this formula coincides with the one used in the previous digest photo production studies. But so what happens is you essentially just cut at certain distance from the source nucleus. But this is quite a crude approximation. So we would like to do this better, and then let's include some or improve this, studying it from the nuclear overlap function, and taking the probability that the two nuclei do not overlap. And we can also employ the photon flux from a wood section source. And so this is given in the thick lines here. But once you apply the probability of no nuclear interaction, but still keeping the target as a delta function, what happens is that you still get a very quick cut at the some distance r, and so it really didn't actually matter what we assumed here, because far away from the nucleus, everything is the same as a point-like source. Now this is similar to what has been applied already in studies of the exclusive processes, where this is actually, I guess, what should be done. But now we are discussing about a inclusive process, where so the dependence on where within the target nucleus the hard interaction happens is relevant. And so let's go one step further and take also this TB from the wood section profile as you would do. And what happens is then that instead of having just this gamma suppression factor in R, this gets convoluted with the TB, and so it gets wider. And so so this takes into account the possibility that the two nuclei are very close to each other, and that the interaction happens at the edge of the target nucleus. And there could be even some contribution from within the source nucleus, but this is heavily suppressed. Okay, so at small r, it is important to take into account the S dependence. And why this comes into play is that, as you can see, the flux becomes a steeper function, and actually a very quickly falling function in R once we go to larger energies. So for some traditional UPC processes which are relatively low scale, actually most of the interaction happens with very small energy photons. But now we are studying digits, so there is quite a large scale involved. So you expect that you have more contribution from the larger energy photons. And so once we now integrate over the R, here we get the photon flux, effective photon flux that just depends on the photon energy or the energy fraction. So, and the results are here. So at small fractions of energy, this is calculated at 5 TeV energy. At 1 GeV, it really doesn't matter which approximation of the photon flux you use. But as you go to larger photon energies, these approaches start to differ just by the fact that you are now more sensitive to the differences here due to the very steeply falling function in R. And now we can apply this to NLO PQCD predictions, and what we see is that within the range measured by Atlas, there are some about 10% effects in the point length versus having the full Wood section approximation. So if we want to do precision physics with these processes, it's necessary to study the photon flux in a more better or in more general terms, not using just simple assumptions. But perhaps more interesting is why this happens. And so if you take a look of what fraction of the photon flux came from small values of R, you see that due to this spectrum becoming more steeply falling, when you are at small photon energies, you have only a small fraction coming from the small distances from the source nucleus. But as you go to higher energies, you need to be very close to the source nucleus to be able to have this high energy photons. And this is the range measured by Atlas. So as you can see, when you go to large values of Z gamma, large fraction of the events actually happen when the two nuclei are very close to each other. And this was not maybe realized by many people yet, that in these digit processes, this happens. And this large Z gamma corresponds to small xa. So if we would like to study shadowing in this process, it's actually complicated by these facts. But this is still work in progress. And the further questions for investigation for me are that what if we have good reasons to believe that this kind of factorization does not actually hold. So then are we actually probing impact parameter dependent NPDFs with this process and not the traditional ones? And if so, we are still working in a more or less inclusive process. Remember that we still have the condition that the source nucleus keeps intact. So in that sense, it's not fully inclusive. So, but it's not exclusive either. So how, if we are probing the impact parameter dependent NPDFs here, how does that relate to the impact parameter dependent distributions that are probed in through GPDs in exclusive processes? So these are still open questions, at least to me. Okay, so this is actually where the EIC comes into a place. So there, the digit photo production is much simpler because the condition for photo production depends only on the electron scattering angle. You don't have to care about any overlap functions, and we know the flux very, very well. And this has been also studied, the prospects of this, and one can see that one probes the NPDFs down to 10 to minus 2. Not awfully low, but remember this is complementary to the PA digits and other EIC observables. So Other options to probe the nuclear gluons at EIC, well, since you have a very good FL extraction capability, this gives a constraint on the gluons. And also, if you use something like charm-tagged cross-sections, this is a well, complementary to the photo production of dye jets. And you can use all of these to study your nuclear PDFs and test whether we had actually pinned down these from the LHC and constrained them further. Okay, I guess I'm running out of time, but let me just remind you that currently most of our gluon constraints come from these measurements at heavy nuclei. And we have from fixed target experiments good coverage of DIS measurements, but only for fixed targets. So we would like to have this at higher energies. And then using heavy quarks and jets at EIC would also give new access to the gluon in lighter nuclei, where we basically have very little to none to constrain our NPDFs currently. So summarizing, there has been a lot of progress in constraining NPDFs with the LHCPA data, but in this analysis we have different methodological choices and data selection, and this causes differences in the obtained NPDFs. Now the photo production process in UPCs offer novel probes, but as I discussed, there are still theoretical uncertainties which actually may prevent us from using them in the actual NPDF fits. So EIC is going to be essential in providing very clean probes and ensuring complementary view from multiple observables to study the nuclear structure. And having measurements with different nuclei is key, because we want to understand how these effects evolve from very light nuclei to the heaviest ones. Thank you.
Thank you for this very nice talk. Any question?
Maybe this question is sort of more for an experimentalist, but since you talked about UPCs, I mean, you talk about theoretical uncertainties, but how, this might be a silly question, how certain are we that a UPC is really a UPC? I mean, it's a classification that basically says that the impact parameter is bigger than the nuclear size. But the bottom line is that the size of the nucleus, but the bottom line is that this is a Bayesian estimate, right? I mean,
yeah.
or is there, I was just, because if we're uncertain about this, there's probably a bigger uncertainty than your theoretical uncertainties. If you have a peripheral but not ultra-peripheral collision being mistaken as an ultra-peripheral collision.
Yeah, so for shape size, for example, this should be quite clear. The detector is almost like completely empty, but then you have to see the shape size. So this is kind of clear. I don't see that there is much theoretical uncertainty, and this is why the experimentalists very much like this process. For the dye jets, I think it's a bit different, because how they define the UPC cross-section with dye jets is that there are no leading neutrons from the photon-emitting nucleus direction. So then what comes into a place, I guess, is probability of electromagnetic dissociation, but that's more of a question of should you include it in your theory calculation or in your measurement try to like fold what you observe with this. So with digits, it's not as clear, but I think it can be worked out.
Yeah, I had a similar question to the digits. So with the digits, as you said, we do cuts that we don't have a leading neutron or something like this. But then you can have that the photon is resolved, and you get another jet from the basically QQ bar pair of the photon. And that is relatively tricky depending on where these particles go to actually veto in the experiment. You can do rapidity distributions and things like this where your digits go. But what was done for the data which you showed, that is was the Atlas data,
Yeah.
I assume, huh? It's still the one which was released years ago, preliminary, but is not published?
It's not published. So
Yeah.
last year they showed new preliminary data, which was now unfolded for detector effects. So there is progress in getting
Okay.
it to the final
Okay.
shape. But for because you are now thinking about where the nucleus that breaks down is going.
No, the photon, you have the photon can be real, and then it has a QQ bar pair.
Right.
And then one of the QQ bar pairs interacts with your gold nucleus, you get your dijet, happy, funny. But then you have the remnant basically from the photon. And that is something which, then it is not UPC anymore, because if UPC requires a photon at a very low Q square, so true, but it requires a photon, not a QQ bar pair. And that is where the background is, and that goes a bit in Giorgio's direction, is very hard to suppress. And I know that Atlas struggled with this.
Right.
I just wanted to know whether they made some progress on that, but obviously not if they still didn't publish, so thank you.
Okay, very good point, yeah.
Concern with, say, extracting, thank you, and PDFs and things, if you're insisting on this collinear factorization, there could be a couple of different things, for example, cold matter energy loss, and possibly nucleon number A enhanced higher twist effects. Are there any efforts to try to maybe include some of those effects and see how this affects your extraction of MPDFs?
Yeah, Francois Arlo has been working on this. I think in the hard probes this year, there was a talk by, I don't know, a student or a postdoc of his who was studying this. So it's, I think, still work in progress, but there are steps taken into the direction. And I think what they saw was that if you include this, they were studying the D zeros from the LHCb, if I remember correctly. And what they see, if you include this effect, then your shadowing is smaller. But they are currently, it was just one observable, and so I guess they are having more work to do.
More questions?
All right. I'm just wondering, this wasn't the focus of your talk, but since we're dealing with nuclei and there is data at x larger than 1, do you allow for x larger than 1 in your parameterization extractions?
No, we don't. So it would be nice to have this, but currently we are having similar cuts on the, let's see where it is, here, similar cuts in the W as the Proton PDF folks use. So I don't remember the exact value, but this basically cuts out our region from x larger than 1. But I saw from, was it the JLab talk here, where they now said that in certain kinematical range, they can, because why we exclude this region is that there are these resonances and things like that, which leads to the fact that it's not just DIS process. So you cannot say that we are probing things in a necessarily in a factorizable way. in the sense of collinear factorization. But what she said was that in certain kinematical range, you still are working in DIS in even very large X. So this was really interesting, and we will certainly study it further. Yeah, so there are some data which go beyond, but I haven't personally looked into those in very much detail, but it's just something that we cannot use now.
So just to follow up on that, if you were to not use it, what part of your result will get adversely affected? What changes in your result by not including those, or not allowing your fits to include X greater than 1?
Actually, if we would like to do that and include them, we would rework our parameterization, because currently we are working in this framework where we just take the proton PDF and then multiply it with the so then we would actually need to change this into some kind of a convolution, as was done by the NDS or some earlier fit. So then we would need to rework also the parameterization.
So that actually is something which for the EIC, you will get a lot of data. And as you know, that Pia has also pointed out that using always the proton PDF as a baseline is not actually the nicest thing. So if you would get really reduced cross sections, exactly the way like you would get for the proton, I think we should really start fitting only the nuclear PDF and not referencing it always to the shape of the proton.
Okay, in principle, so if we had only nuclear data and we fit those,
yeah,
then this makes perfect sense. But since we are actually using quite a lot of data from PA collisions, both fixed target and now LHC, then you have to include in your analysis the proton PDFs anyway.
Yeah, true.
So,
I know.
so the thing becomes more of a how you treat your uncertainties. And actually now both us and NNPDF, we study the correlations of our uncertainties with the free proton PDF. So whatever way you will parameterize your NPDFs, this is just a parameterization. You can you can basically do whatever you will to get this thing. And then the thing to be very careful about is to study all the uncertainties that enter your fit, whatever you are fitting.
Yeah, and some of the NNPDF nuclear fits have uncertainties you cannot believe, even in NNPDF, because they were so small, even though they use only a very small, less data than normally. So I think for the EIC, it would be really nice to see, because it's DIS. Just take the reduced cross-section and see what comes out with this data and compare to. I'm not saying you should abandon this completely.
Yeah.
That would be crazy. But just for the systematics to see what would happen.
Yeah, exactly. And I think some proton PDF fitting groups have done these studies that they only take the HERA and HERA and fixed target, or only collider, see how these effects depend on your choices. Yeah, exactly.
Yeah, I think I want to underline that. We did all of these things with PA and everything because we never had a pure EA data set. That's what we're going to have. So it actually makes a lot of sense to start thinking about doing only EA fits to start with and then include other things. So we want to underline that.
Yeah, of course, we still need to wait a couple of years to be able to do that, but yeah.
Okay, let's send the speaker again. Okay, continuing with our program today, we have now Fernanda Stephen. She's talking about PDFs, GPDs, and TND PDF from Lattice QCD.
Okay, thank you very much for the organizers to invite me here. It's a special pleasure for me to be in this place in particular because I worked many times at the old institute here. It's the front house where the cafe is. Used to be an institute of theoretical physics for many years, and well, lots of change since then. But anyway, so today I'm going to talk or to give an overview of the work we have been doing the last 9 years, maybe since 2014, when we first tried to compute PDFs from first principles. Most of the work is done in collaboration with the ETMC people, which are most of them only recently. You have all the collaboration with Andreas and Shoini, who was at BNL, now it's, sorry, at Temple, now it's at BNL, and now it's Fagato also at BNL, and more recently Young in Argonne. Okay. So let's see. Yes. So just a quick reminder to everyone, although we saw in many different aspects of these quantities here during this workshop conference. So we have the twist two-part distribution. So the complete set of the distributions comprise the unpolarized distributions, the F1 that I'm calling here, the velocity distribution, the G1 gives the spin distribution, let's say, and the transversity distribution, which we call AG1. So all of them can be measured. Well, you can compute them in principle. You know, formally they are given. For example, for the unpolarized, formally it's given for a correlation on the light cone of objects like these ones here. Just very simplified here. No Wilson line connecting the quarks. But in principle, they can be computed. They can all be measured. Okay, the polarized and elasticity both can be measured in a totally inclusive process because they are chiral even, but not the case with the transversity one, which is hard to measure. And of course, we can get data from lattice for that would be very helpful. Also, you can have beyond twist 2 distributions, you can have the twist 3 distribution. So just to remind everyone, the twist, you can look like a power. Take, for example, the unpolarized distribution. It can be like a power expansion in the inverse powers of the relevant scale for the process here, that in the case is the momentum transfer. And just to take the twist 3, the analog of the 3 distributions that you saw before for the twist 2 are the EX, the GT for the analog of G1, and HL would be for the transversity 1. So they have no density interpretation, as I write here. However, they can take other information that is not available in the twist 2 distribution, like possible quark-gluon quark correlations, possible zero-mode distribution. That is, there was been a lot of discussion lately about those contributions, and they are relevant in many different aspects. For example, there is this proposal by Matthias that can be interpreted as transverse force acting on the quarks being scattering in the case of GT. We can test the Van Dura-Wilczek approximation. Okay, there are some analysis of the data that allows something like 15 and 40% violation. We can test the Burkhardt-Göttingen sum rule. We can also test this relation here between the E twist 3 distributions and the pi-nucleum sigma term. So there's a lot of physics there. So for the case For the case of GPDs, well, I'm not saying much because I think there were so many talks here explaining GPDs. So here in this particular one here, I'm showing the process where is a deeply virtual Compton scattering, where a virtual photon is exchanged, and a real photon is measured in the final state. And these distributions, they are not unidimensional as the part distributions that depends only on the longitudinal moment or the fraction of the longitudinal momentum of the quarks, of the proton carried by quarks, but they depend also on the momentum transfer. This is not good. The momentum transfer between the initial and final states, which are called delta. Also, the fraction of this momentum transfer, which we call skewness, psi, and depend, of course, in x. So they are multidimensional objects, and have been said here many times in different limits. For example, if you take the limit of t going to 0, xi going to 0, you have just normal PDFs. If you integrate over all x, you can have the form factors and so on and so forth. Okay. So finally, to complete this let's say three-dimensional view of the nucleon, you can also have the transverse momentum dependent PDFs. Here they are represented in one particular process, which is the Darwin process, which if you measure this momentum of the lepton pair produced, then you can have access to this to the distribution depending not only on the momentum in the longitudinal direction, but also the momentum of these partons in the transverse direction. So this is the whole picture. So my talk today here is going to show you a bit of what we have done for all of these quantities over the last 9 years. Here, just for completeness, I put here in case someone is interested in download the talk later and have a look. The most important papers, I would say, or the papers that are seminal papers in the proposals for computing these things in what we call the quasi-PDF approach or pseudo-PDF approach, and the first calculations that we had, and then the calculations we have at the nucleon, at the physical biomass, also the first calculation GPD, and recently the TWIST-3 ones, and TMDs that is just starting right now, and I will show you today here some preliminary results that we have on that. Okay. So very well. So light cones, PDFs, and I don't know why I'm looking there. Better look here. Light cone PDFs and quasi-PDFs. Okay. So as I said before, the light cone PDFs, the PDFs are given by a correlation, light cone correlation, which is represented here by this graph that I drawn here. And in principle, you have to compute objects like this. That is the quark and antiquark separated on the light cone by the distance z minus, and a Wilson line connecting them to make this object gauge invariant. Okay, so our focus is the isovector one. So the thing is that, okay, how can we compute these things? Let's have an example here, like do a perturbative calculation of this object. Suppose you want to do a perturbative correction to that light cone correlation that I showed you before. So in principle, yes, you can do. I mean, you can have a bare distribution, and then you do the dressing, the perturbative dressing, depending on some regulator here, lambda, which I will call lambda. It can be the infrared or the ultraviolet, doesn't matter right now. And so you have when nothing happens, so you have the self-energy correction, which are called pi, and you have the vertex correction, and so on and so forth. Then the higher order corrections, and you have target mass corrections, you have higher twist corrections that we just forget about them right now. Although in our computation we include them in the end, but for this example, we just forget about them right now. So you can dress it. It's something like this. Okay, so you can do this calculation just to show you a very simple one for example, for the very simple diagram, you can have it's something like this. So you can be written in terms of the light cone coordinates like this one here, where the small p here is the momentum of the quark before the blue emission, and psi here is not the skewness. In this case, it's just the fraction of the parent proton that this quark here is carrying before blue emission, and after blue emission is momentum k. So you can do this. You can do this integral. Have these two poles for this1 and this1, and it happens that if these poles depend on y, so the y is this momentum fraction that I'm putting here. So if y between 0 and 1, one pole is in the upper half, and the other pole is in the lower half. Okay, so that means they contribute. Now, if y is bigger than 1 is smaller than 0, the poles are either in the upper half or the lower half. So it means you can integrate them out to 0. So you have then contributions. You have then something like this, an integral like this. You can use dimensional regularization I'm using mass as quarks here, and then you can use dimensional regularization to regulate both the infrared and the ultraviolet. And you do that and you get something like this, okay? So where mu is the scale associated with the ultraviolet, and mu f is the factorization, we call factorization scale, so associated with the infrared of the lower scale. Very well. So you can do, okay, this has support only the physical region as it should be. So you can do actually the same calculation in the infinite momentum frame. So now you write something like this. So instead of having the momentum on the light cone, you have the momentum in some specific direction, okay, the third direction here. So you have again these poles, you do the calculation again, and you get something like this. It's exactly as we had on the light cone, and you have this result exactly as before. So saying what we all know, that the light cone and the IMF are completely equivalent for this calculation, so they should be the same. Unfortunately, these objects cannot be computed on the lattice. First, because I cannot do a real-time simulation of the lattice, so the light cone is out of question, and I cannot put an infinite momentum on the lattice, which is also out of question. So the question then, what if P3 is kept finite? Okay. Let's suppose P3 is kept finite, so it's not in the infinite anymore. So I do addressing again just to differentiate with I had before. I put a tilde here just to say, okay, we're having this P3 finite and not infinite now. And I do the dressing again, okay? So doing that, P3 finite, I get again something like this, and do now the integral. So the thing is that I can do the integrals on P0, keep P3 finite. The integral still has the infrared divergence, but the ultraviolet divergence are not there anymore. So the P3 actually is acting like a regulator, effective regulator for the ultraviolet. So the results I have is something like this. So besides the contribution in the physical region, I also have contribution in the unphysical region. But, okay, the poles, if you remember the results I showed before, the poles in the infrared are exactly the same for the both cases. So that's saying the following. It's saying that the difference between keeping P3 finite or infinite is just in the ultraviolet. Okay, so then I can, in principle, let's say I want to start with something I can compute in the lattice, something like that. This proposal that's the original proposal by G 10 years ago. And what I want in the end, it's something like this. So I have to go from here and come here. So what we can do then is like we can boost this guy to P3 large. Of course, you cannot go to infinity, so that we are somehow closer. It means that the difference between the finite P3s that we are having, large but finite, and the infinite P3, in principle, can compute in perturbation theory. That is just this calculation I showed before. So you can actually compensate these things. You can actually compute this guy here, with the boosted one, and then take the perturbation theory to take into account the fact that you cannot go to infinite boost. You just cannot do that. So what you end up then is something like this. Here I'm calling it age, just not to say this only for PDFs, but also for GPDs or TMDs, you can do something like this. This is basically saying the following. This process is saying that, okay, I can compute these things on the lattice. I can actually compute these things in perturbative QCD. That's the calculation I just showed. And then I can extract this H, which is the light cone one. So this is the factorization that we are using here. So just I saw in one of the talks a few days ago, saying that in a way that's as a bad thing, saying that LATSI doesn't have access to real-time correlations. Okay, this is true. We don't have direct access, but neither experiments have access to them. We rely on factorization theorems in both cases. Here, okay, this guy is like our lattice observable, and we use factorization, and you compute this guy, and then we have access to this. In experiments, you compute cross sections. You can express them in terms of structural functions, and then you apply factorization theorems to get the same thing. So it's exactly the same thing. It's not the physical observable that you're measuring in the lab, but is the lattice observable. Okay. So this is the idea behind of the whole thing I'm going to show you today here. All the results I'm going to show is basically based on this factorization that I show you here. Okay. So very good. So some results for this too. So I don't go through all the things, how to get there, all the details of the lattice calculation and so on. Just to show you here some results for PDFs computed using this procedure of quasi-PDFs that I just showed to you. In this case, using a lattice at the physical biomass. This L here is the length of the lattice, and A is the spacing between the lattice points. Very well. So here I show the results for the unpolarized elasticity. This is the nucleon boosted. And the third direction is 1.38 GeV, which that is 10 pi over L. That corresponds to 1.38 GeV for these configurations here. Here is X, the momentum fraction carried by the Spartans. For positive X, it's what we the usual quarks, and for negative X is the anti-quarks. So this was the first calculation in the physical biomass published a few years ago, and I find it very remarkable that we are so close to the different parametrizations for these isovector distributions, given that it is purely QCD. You have no input here other than when we preparing the ensemble that you are using there, we fit the mass to reproduce the mass of the pion. And so very well, so we can compute these objects. These objects can also be computed in the pseudo approach, here separated in the quarks and anti-quarks. The pseudo approach is like the quasi-PDF approach, just you do a factorization in the position space, and then you write things when you factorize the position space in terms of some distributions, depends on the off time, so the off time distribution. So you do the Fourier transform of this off time to the momentum space, wax dependent, and you get some things like this. Very well. So we can do the same for twist tree, okay, as I just showed you. So here is the result for the twist tree. This is in blue is GT. In the yellow orange here is G1. So that is a nucleon boosted at 1.67 GeV. So first of all, the BC subrule is verified. So the integral of GT is equal to the integral of G1, very well. And the WW approximation, the Van Durack-Wilczek approximation, which here I'm writing in this way here. You can see here in purple and yellow is the Van Durack-Wilczek approximation used plotted using parameterizations for G1. And in this case here is the Van Durack-Wilczek using GT, and GT compute directly from the lattice. It's a very good agreement in this area here. In the large X region, there is a violation of 30 to 40% is possible, and this is actually also in line with that experimental analysis of experimental data that I show you earlier, that I mentioned to you earlier on. We can do the same for the twist tree, for the chiral one. So you compute HL, and we have the Van Durack-Wilczek approximation for the case of HL, which is given by this expression here. So the twist tree determined from the twist 2 distribution H1. So in purple here is the WW approximation use the gem, and the others, the yellow one is computing using the data for H1 that we have, and this HL that we compute the lattice. Okay, so suggested twist tree distribution can be determined from its twist is a missing twist 2 counterpart. Very good. We can go on and go for the twist 2 GPDs. For the twist 2, we use a different ensemble because the simulation is very costly for the case of GPDs. So it's a heavier than physical pile mass. The case here, 260 MeV. But anyway, so let's see here what we have. So these are the results for the GPDs for 3 different boosts from 0.83 to 1.67 for a momentum transfer of 0.69 GeV for 0 skewness. So you see that's more or less stable for H, and also, but not for the case of the E GPDs. Okay. We also computed the H for just for the largest value of P3, and compare the H with the corresponding, what would be the corresponding in the limit, would corresponds to the F1, the unpolarized distribution. So that's the difference between them for the case of psi equal to 0. And here we have the same calculation, but just the effect of skewness. Okay. And actually, we see that there are these points here are these points that skewness equal to 1/3, which actually we have discontinuities in this point for the case of the positive X. Okay, very well. So, well, we can also have the case of, we also compute the case of G1, so the polarized H or the helicity H tilde GPD, and here compare with the analog, the PDF analog, which would be G1. Okay. And here also we have results for the case of non-zero skewness. Okay, so very good. So as I said before, the problem with GPD for the simulation is that the calculation is not very efficient. So, so we are basically computing something like this, where the moment that is transferred is symmetrically shared between the incoming and the outgoing hadron. Okay. So what happens is that when you do the simulation, we have a source and a sink on the lattice. So because it's symmetrically distributed between the source and the sink, so you have different momentum here and there, it means that we have to do a separate calculation for each momentum transfer. So if we change the momentum transfer, we have to change the inversions, the propagators, because the moment changes not only here, but changes here too. It would be much more efficient if we had a fixed moment in one of them. And so in one of the ends. So in principle, you can do that using this kind of thing. I mean, you can, instead of using a symmetric frame, you can use an asymmetric frame, which actually this was the first, when Raduskin talked about GPDs in the late 90s, he was actually the asymmetric frame, while G was in the symmetric frame. So the thing is that, okay, can we go from one to the other? Well, in principle, yes. Okay, so you can go from here to here. Remember that the momentum transfer is on the transverse part of the momentum. So we can have a transverse boost connecting these two guys. And the thing is that the zero component of the symmetric here, it receives contribution from the zero of the asymmetric, that is one, and the transverse one. And the same for the transverse heat mix. So that is basically saying that, you know, your Dirac structure computed on the symmetric frame for the asymmetric frame would have contributions not only for the zero component, but also from a Dirac structure in the transverse part. Very good. So historical definition of quasi-DPD. So here is a matrix element of that you can decompose it in terms of quasi-GPDs. And you can decompose usually in terms of H and E, as usually done. Here I'm using curly to say that these are quasi. When I don't use curly, it's not quasi, it's a light cone. So the curly for quasi, and this zero here is for the original historical definition of them. So you can do this thing for the symmetric and for asymmetric. So you have H0 and E0 for both cases. So you can compute them, and we did that actually. So here is the blue is the non-symmetric, the asymmetric, and red is the symmetric for the H, and here is for the case of the E. So we see that there is a frame dependence. So we are actually seeing that the usual way you decompose the GPDs in terms of H and E is not large invariant. There is a dependence there. Okay, so we have to fix that. So there is a frame dependence. And that's basically saying that these base vectors that we are using before to do the composition, that is in terms of gamma 0 and sigma 0 b, does not form a complete basis, okay, for this, especially separate bilocal operators at finite momentum. Very well. So what we did a new parameterization. So instead of actually two form factors, if you do the composition in the positioning space in the Lorentz invariant way, you end up with actually 8 form factors, okay, and not only 2. So you have actually 8 Lorentz invariant amplitudes called AI, which depends on Zp, Z delta, T, and Z squared. So on the light cone case, well, in the light cone case, that should not happen. So in the light cone case, you just should be for the symmetric, and for the asymmetric, you just have just this decomposition here, which you can actually relate this decomposition with this one here, and the usual age of that everyone talks about on the light cone, it can be written actually in terms of H1 and A1 and A3 of the very general one. Okay. And we can also make this object here, Lorentz invariant, just multiplying by Z in the numerator and denominator, and you have something like this. So this would be the relation between the usual light cone H and A. 5 minutes. So the quasi case, if you do something similar, you end up with these horrible expressions here, which is basically saying that you have manifestly non-invariant kinematical factors multiplying all these things. And However, when you go to P3 to infinity, you have to go to the light cone. When you do that, we actually reduce the light cone result in the infinite momentum frame. However, we are also always dealing with finite momentum, so we have to be careful when doing these things. So we can actually extract these things on the two frames. And here, forget about this one, just the leading one, the A1 and A5. You can see that, for example, the light blue and dark blue is the symmetric and non-symmetric for A1, and here symmetric and non-symmetric for A5. When you do that, you see that actually A1 and A5, they are actually frame independent. So we can, in principle, compute H and E in the usual symmetric frame using the AE calculated in the symmetric frame. So because I don't have much more time, I'll just skip some of the results I want to show you here. And go to the most recent one, that the TMD PDF. Okay. So the work I'm showing here is basically based on this paper we published last year, and the last proceeding of this last conference we had in Bonn in August last year. So one is for the soft function, the other one is for the beam function. Should be very clear what they are. So TMD PDFs, how to define TMD PDFs? Remember, we are doing that one loop correction that I was showing before. You can do something similar for the unintegrated. So you're not integrating in momentum here. So L here is the momentum of the gluon, which is going there. So here is the gluon emitted by the quark line and absorbed by the Wilson line. So you actually do this calculation, you see that there are three divergences. There's the usual ultraviolet, there is the usual infrared, and there are the soft gluon radiations, that soft gluon singularity that is basically when L plus here is equal to 0. So this extra divergence comes basically from the coupling here to the Wilson, to the light-like Wilson line. You can actually rewrite them in terms of what we call rapidity. So you have a rapidity divergence actually, which for the usual PDFs we cancel with each other because there is a cancellation between the vertex and or the real and virtual corrections, if you will. For the transverse case, this cancellation, it doesn't happen. So, and actually you have then extra divergence, that is the soft divergence, that we have to do something like that. So usually, to make a long story short, we absorb all this, the soft relation to soft function that we have here. And because this is a light-like Wilson line, and we have this divergence, so in principle, you have to find a way to redefine things. And actually, one do. Basically, here is the function I had before. Here is some soft function that is in terms of those rapidities that absorb this the soft gluon singularities. And here's the unsubtracted thing that besides the soft gluon, you also have all the divergence you have to take into account. Okay, so basically on the lattice, you have something like this. We have the same as before for the PDFs, it's just that the Wilson link connecting the two quarks actually is like a staple shape now. You go to some direction L, you make a movement in some direction, transverse, like it's here, transverse here, and then you go back in this length L. Then you have something like that, okay? Very well, and this soft function here that has all these divergence, in principle, you can rewrite them in terms of, we call a rapidity independent SR that we can compute in the lattice, and in terms of the Collins-Soper evolution kernel. So when we do that, we have a similar matching equation that we had for the quasi GPD and the quasi PDFs. We have something like that. It just not only the perturbative matching kernel we had before, but we also have dependence on all these factors here, which is the Collins-Soper evolution kernel, the Collins-Soper scale, and this soft function that's there. Okay, these objects, they can be computed. This can be computed in the lattice. I'm not showing because it's a long story on all the details to get there, and these guys can be computed on the lattice. Okay, this is the result we have for the soft function as a function of the transverse separation between the quark and the anti-quark there in the staple-shaped link, which defines the TMD PDF. And we also have computed this beam function that is that correlation with this staple-shaped link. And you can see here some first results where there is an L dependence that is basically saying that there is a divergence related to that. We actually can cure this divergence. There are a lot of other divergences, which I just point here. You can cure all these divergences. We are finishing a paper just to saying details how, in the case of the ATMC, we can do a non-perturbative renormalization to take care of all these divergences. And then once we have the renormalized beef, then you put together with that soft function I showed before, and then you can extract the TMD, or let's say the light cone TMD itself, as is our objective. Okay. There is one first result for that is from LPC that was just released a few months ago, not yet published, where they do a similar treatment, and I show here their results, that is this blue here as compared to some parametrizations, by using different values of PT. So just to summarize, so there is huge development of first principles of PDF, GPD, and TMD PDF. I was just talking to Tony the other day. Tony was my supervisor of my PhD. And I was telling him, no, Tony, I remember when I started working with you many years ago, and you asked me to compute a few things. One of the things you asked me first is to understand the higher twist contributions and how to compute that. And at the time, I had no clue whatsoever. And I think that all my life would be without computing them. And now, finally, after a few decades, we are basically getting there. So we have some first results for twist tree, for GPDs also, and the TMDs are on the way. Okay, so of course, much more work has been done. There has been work in pi and k PDFs, and meson distribution amplitudes, in delta PDF, and glue PDF, transverse GPDs, also synergy between lattice and phenomenology, using lattice data at the same foot, experimental data to do the fittings of the data, and there are many improvements to be done. So just to finish saying that it is a very exciting time to be working on this field, as we finally are being able to compute these non-perturbative objects that are input to so many calculations from first principles. Thank you very much.
Thank you for your very nice talk. Any question?
How much more complicated would a deuteron be? Deuteron, like...
The nucleon.
Yeah, like lattice nuclei.
The nuclei, to do for the nuclei.
Yeah, let's start with deuteron.
Well, in principle, I have not thought much about that, but in principle, you can do something similar. You have to design a factorization. You have to factorize this object in terms of how you define the PDFs in the nuclei. If you can do that, just lattice observable, you factorize just what would be the PDF in the nuclei, and there is a factor that you can compute somehow or structure somewhere else, then you can do it. This is the same thing, because you end up with a correlation here, just because your state now is probably a bit more complicated, okay, but not yet there, okay?
Yeah, I was maybe wondering in terms of lattice computation, how much.
Yeah. From the lattice point of view, probably more costly. Yeah.
Other questions?
Fernando, so this one told you you had problems, right, with, you showed us you had a set of form factors, and then you had the frame dependence, right?
Yeah.
And then you went to another one. This was just Lorentz, improving the Lorentz invariance, or did you have a problem on the translations?
Say it again, sorry.
You had a frame dependence.
Yes.
This is going from one frame. This is a problem of just Lorentz invariance or Poincaré invariance?
I think it's a problem of Lorentz invariance.
Mm-hmm.
Okay. I think.
But anyway, you tried another set and then
Yes.
worked. Okay.
Other questions? Okay, if there is not, let's send Fernanda again. It is time to coffee break. We back 11:10. Souter. He's going to talk about vector meson production at large T and AA collision.
Good morning. I thanks the organization to the opportunity to talk about this work. Okay, this presentation is divided by an introduction. We'll talk about the motivations about this work, the formalisms, and the results and conclusions. Okay, the motivations of this work is study diffraction process with rapidity gaps. I interested by the exchange of BFK polymer in high momentum transfer to study the QCD dynamics LHC now in Electron-Ion Collider. Well, we have several works with Vitor Gonçalves in that we studied the production, diffraction production of vector mesons in hadronic collisions. We also have with exchange of a polymer with high T, with high moment transfer. We also have a work with the same process with the production of photons. My motivations for Electron-Ion Collider is consider the production of vector mesons as observe our QCD dynamics, linear versus non-linear dynamics. The linear dynamics encoded by BFK equation and mainly non-linear dBk equation. Well, we have a clean, in this process, we have a clean experimental signature. We have more precise kinematic variable determination than here. Here, measure this process. We have in here we have limited rapidity absence. In electron-ion collision, we assess a new kinematic regime in electron-ion scattering. So we do a very quick calculation. Exchange the hadron collider for our electron and maintains the other hadron as projectiles. Well, this process can be separated in several parts. We have an electron that emits a photon. The photon splits in a quark-antiquark pair. After the quark-antiquark pair forms a vector meson. The quark-antiquark will exchange a pair of gluons in singlet state. We now interested to study these dynamics. We consider in previous works two gluon exchange, but we interested to consider a polymer exchange, BFK polymer exchange. Here, in this diagram, we have now is not in the figure. We will not put them, but this vertex is the effective vertex, the Lipatov vertex. The vertical gluons is regionalized, and this pair of gluons will interact with one parton in the hadron. As we consider the large momentum transfer, this target will dissociate. Well, and also this class of projects, we have a rapidity gap, a meson, a rapidity gap, and the remnants of the target. We do a formalism which was developed some years ago by Forshore, Riskin, Bartels, and others, Zemberg, Mochica. And we also consider we use this present calculations is based in these works. There are J-psi productions and PA collisions by Frankfurt and others. And more recently, Kotkan and others consider Pomeroy loops, same process, okay? But we consider the exchange of two BFKL Pomeroys. We have also, for AP in Electron-Ion Collider, a similar result by Dix, Tatsto, and Strickland. Well, so we calculate these cross-sections, consider particle production in photoinducted particle production. The coherent production is considered in a hadron. Photon, the coherent is considered this one. The hadron produces this photon in the form, in coherent form. Okay. Well, we also consider the presence of rapidity gaps. We also consider the large momentum transfer, the dissociation of the target. We also consider, well, we talk about and consider the Pomeroy BF Pomeroy extension. Of course, this BF-KL Pomeroy we will consider only in leading order calculation. As the same form, the BF-KL Pomeroy extension have a limited kinematical window. It's expected the Pomeroy extension not describe all the data because we don't have in high energy we expect non-linear effects. In the BF-KL is a linear equation. So we have to calculate different and total cross sections. We consider integration of a different cross section. This different cross section is a convolution of the gluon and quark parton distributions with a partonic cross section. We also consider a total cross section in several intervals used by the experimental collaborations. This could be done because the Pomeroy couples with individual parts of the hadron. Well, in the previous results, we use using this for the PDFs, we use CTEC6 for method vessels and MSTW for photons. We use EKS for the ion-ion case. The parton distribution, the parton cross sections, a partonic cross section, differential cross section, is given by the BF-KL formalism. We have a amplitude square amplitude here. In the meson production, I put here the final result. Is the same, is the usual result by these formulas. Here I put the final result with these expressions of these quantities, which is related by the impact factors of the transition gamma to vector meson and quark to quark. This is related by this part of the Feynman graph and this part of the Feynman diagram. This expression here is calculated at leading order. There are exist next leading order calculations of this quantity, which I will not use in this work. So here I include the quark impactor is given by usual expression Miller-Tank. So you put all together to calculate these quantities. Here we have interested to the TCD dynamics. So this is included in this function. This function is a BFKL characteristic function given by dBFKL equation, which can be in leading order calculation is given by this expression, where psi is the d gamma function. All these results here we not use next leading order calculations. We use only this one calculation. So we have in this amplitude we use we do a consist calculation. We consider here leading order calculation, here leading order calculation. So in this order we have some problems. In the expression we have a energy scale here. This in leading order calculation, this is arbitrary. Alpha S, the running coupling constant, is fixed at leading order BFKL. This expression. And so, more important, the power growth of this expression with the center of mass energy eventually violates the S-channel unitarity at larger rapidities. So this gives this is a very important problem in the BFKL approach. So we can use to solve this the original consider as, for example, next leading order BFKL. We don't do that here because this expression given by Fadin and Ciafaloni gives a extra term in alpha S square here. Is a very lengthy expression and also have some problems. We have one of them is the choice of an scale, other is the renormalization scheme because now we have alpha S square calculation, and more important, gives a large and negative correction to the characteristic BFKL function. So we can also consider in these words, but I don't display here, two alternatives. There are other ones in the literature. We consider Brodsky, Fadin, King, Lipatov, Pivovarov alternative. We use the BLM optimal scheme, and we'll also use a different renormalization scheme. We also consider in this word, but not in this presentation, the Sabio-Vera all poles next leading order BFKL. This is a collinear improved BFKL kernel characteristic function. We have a sum, a resum of collinear effects. It's a very complicated expressions. It's a very complicated point to consider here. Okay, we use also only here next leading order BFKL equation. We also we also consider, we consider consider this leading order equation. We consider leading order characteristic function, and then this is a leading order result calculation. Well, this is very, for vector mesons, this result depends strongly depend on the several parameters. The coupling constant we consider fixed to do the fit with the Hera data. The best we found is this one. There are very different energy scales in literature. We consider this expression where we consider the square of vector mass plus the a constant plus the square of momentum transfer. So we have these parameters. We use this one form. So we put all the impact factors in BFKL, kernel, and leading order. We could use next leading order correction, but it's a guess of the result, because we still use the next leading order form factors. Then we show here, but we use only the leading order results. Well, this we have three parameters to fix: alpha s, beta, and gamma. We will fit the Hera data to fix these parameters and use them in the other results. So we done this here several years ago. For J-psi, we use Zeus and H1 and data, and we consider different forms of the scale, energy scale in alpha s. We have a good agreement with the data, with this data of differential cross section as a function of the square momentum. When we use this choice of parameters, and so we use them for the other results. So we also do the vector meson with the total cross section for vector meson with these parameters fixed. We use a different choices, intervals of integration in t variable. These intervals is given by the experimental collaborations. And when we use the fixed parameters and do calculate the total cross section, we have a is a good agreement in low t, and not so good agreement in large t for the total cross section as a function of energy photon proton, energy of mass of photon proton collision. When we consider hadronic collisions, we use a convolution of the photon number of photons in the target, and we convolute with the total cross section as a function of t to give the different cross section as a function of the rapidity. So we use this here. Okay, we now we use this. We have two hadrons, so we have a symmetric collision. We have the photon could be coming with this hadron or this hadron. There are three possibilities. We have a proton collision. Could be with proton collision. We have also nucleon collision and proton ion collision. Okay. For the Fockman flux, we use the well-known expression of Dres, Semberfeld, and al. For the nucleus, we use the original Weizsäcker-Williams expression with when the nucleus is a point charge. Okay. Here we have a modified Bessel solutions, and is the very known expression. So when we use when we calculate this with the same parameters fixed by the previous results, we have for J-psi collisions for next to leading order BFKL, we have this rapidity distribution for usual LJC PP bar energy. We also consider the lead-lead collisions. We have an improvement in the as is expected. We have improved in the cross section. Okay. For different large G intervals. So we have also considered in proton-lead collisions, we consider the production of J-psi mesons. We use the same parameters in the same intervals, and we do a comparison with Born order, two gluon exchange, and the next leading order BFKL. As BFKL, we have an improvement in the S dependence. We have a different behavior in the center of mass energy. Here, we have the two gluon exchange considered here is a constant. We don't depends in anything in the energy. It's a typical of two gluon exchange. And we show here that there's a very different behavior in the rapidity, in the interval rapidity. In black, as for example, the red one is slow than smaller than black one. And this behavior is the same for any processes. So we have this is idea. This is the main interest here to check this difference of this dynamics, QCD dynamics, in this type of hadronic collisions. For electron-ion collisions, I do a very simple calculation. We consider the same calculations as hadron-hadron collisions with the same parameters fixed by the Hera delta, but we replace the proton PDF by a nuclear one, and then you use three more recent PDFs. And also we change the photon luminosity. Here in this plot we calculate electron-lead collisions. Here we use the LPDF interface to calculate the PDFs on the nuclei. Yeah, here we also put only a comparison with these different nuclear PDFs. So we also consider electron photon flux given by Friccioni in all. We have a very known results. And so we do this, we perform the same calculations, we have obtained these very preliminary results only to compare with our previous results. We have here a different cross-section as a function of the momentum transfer. We consider two different energy, center of energy electron proton, center of mass energies of photon proton collisions. We use 10,000 GeVs, 50 GeV. We have a very, there are not a very different dependence on the nuclear PDF. So, but we have also, if you consider in the previous results, we have a quite near result here. Okay. So these are very, very preliminary results. Okay. So always to check and see if these formulas can be used here. We also consider total cross sections. We use the same intervals and PP and PR collections to do the comparison of the results. As the different cross section, the total cross section, we have a similar results as a function of the photon proton energy of center of mass energy. We also included calculate the same as the rapidity distribution. We consider here a limited range of rapidity. We don't have a symmetric one because we don't have the photon came only from electron from the electron side of the process. So we have some conclusions on this work. Our results shows that BFK formalin is able to describe the current experimental data for AP collisions for Hera. Okay, with a choice of or a fit of the parameters. We also show that PP collisions in LHC is able to constrain the QCD dynamics. This process can be complementary to recent theoretical and phenomenological studies that use next leading order. We don't show here, but can be used also to study this QCD dynamics as virtual photon collisions and Miller-Navelé jets. This exploratory analysis done here is useful also to indicate the potentiality of this process to probe BFK dynamics as well as to constrain the influence of higher order corrections. We don't do that here because it's a very, very preliminary one result. We also pretend to study the conformal spin. The result of BFK always is a series in this quantity. We expect that this is a very small effect. So We also consider next leading order BFKL expression, but as we talk about, we also need to include the form factor, the transition of the meson, photon to meson, only as the same order of the calculation. We also include consider different nuclei. So, thank you for attention.
Thank you for your talk. Questions? No question?
Do you have an idea of what in this list is more sensitive to BFKL dynamics? You have considered EP, then PP, and we are going to Electron-Ion Collider. And also there is all this famous work about the Müller-Navalle jets, which, by the way, if you could comment on their results, I appreciate, because I know that it dedicated many efforts to understand this and compare with data. And now there are data. So in short, where is the best place to look for BFKL dynamics?
Well, I don't know. This result is very okay. Müller-Navalle jets is a very task one is not easy to obtain results. Okay, we have we expect in the next colliders we do more sensitive measurements on this observable, but I think that for this process is a very good. Okay, it's a good place. It's not a very good place to do that, because we have several things to. All the ingredients is under control, or maybe almost control. Let me do that. Here. This is okay. This is it's a well known. This could be calculated, and we put this consider this calculation here. We also consider this in the experimental point of view is a clean process. We have two rapidity gaps and so on. We can do.
Very nice. Quick question. From your studies, can you tell how far one can believe or trust in linear BFKL, and at what point from what you do, can you tell whether you reach the nonlinear region at some point? Can you estimate where that could be?
You mean the validity of the linear dynamics? Well, I think that we need to study this to discriminate where the linear and non-linear regime is valid. I expect that in large energies we have a linear non-linear effects. Okay, but we can need to use the linear description to study where one is valid or not.
So I want to take this a little bit further from the experimental side.
Okay.
All these activities are very important for us as we are approaching the realization of the collider.
Okay.
Currently, there are only two Monte Carlo generators are being used for most of the studies. One is called a Beagle and one is called Sartre. Sartre is mostly diffractive EA, and Beagle is DIS, but it's a very homegrown kind of an effort. The effects that you have presented here are very valuable. I think we need to know them to catch them in the experiment. Is there, I mean, it can be a suggestion or a question. If you can have people working on these in the and produce or contribute to those Monte Carlo generators to make them more general or more effective, that would be very valuable. Do you have any ideas about that? Or those can be local collaborations here. If you have students, postdocs working on it, you can expand on those things and make that. Have you thought about such?
Comment.
Other question or comments? Okay, let's send the speaker again.
Thank you.
Now it is time to closing remark in charge of Professor Abay.
All right, so I'm going to make short remarks. I'm not going to keep you from your lunch and the end of the meeting. Those 4 remarks I want to make are with 2 different hats on my head, or actually 3. The first one I want to make based on my role in the International Advisory Committee, IAC, of this poetic meeting. I think that the recording, the scientists, the scientific talks, the discussions that we have had here, including the wonderful posters from students and postdocs outside, were of highest quality. There was some concern about, that not too many people coming in here, but I think it worked out beautifully with the level of discussions we've had. Was absolutely fantastic. I've attended, this is the 10th poetic. I've attended the previous ones where we had 170 people, and it was run like a meeting. It was like a conference where there was unfortunately no time for discussions. So having this group of 50 theory and experiment together is an excellent thing, and I think this was really well achieved here. And particularly, I want to commend the questions that came through. The enthusiasm I saw from the students and postdoc was really important. Okay, now I take that hat out and I put the hat of the EIC science director. So EIC is going to happen in the next 10 years. We hope that the whole funding level will not change. DOE is very concerned about not changing it because we want to keep it on that schedule, because every year extension is a very large extra expense on the total cost. So DOE is doing everything possible to keep it on schedule, which means that anything that we get to contribute, we have 10 years to get there. So the theory community here is extremely involved, as you could see. That I don't have to tell you that. They are very well connected to the EIC science. But also I heard that there is a desire to go in the experimental direction. I think this is a very important thing. If the expansion of the entire QCD community has to happen, it cannot be only theorists moving forward. It has to have a very strong experimental component. And I think as a community in poetic, do everything we can to not only expand and support the theory, but also the experimental effort. And Elke told me she had a fantastic visit yesterday to the light source. And I'm sure now, based on what she told me this morning, I think we will have a large connection to the accelerator science towards direct components and input towards the design and construction of the EIC. I think this is what she came back with, and I think this is not a surprise to me, knowing it's a 4th generation source and all homegrown components are going to be very valuable, I think. So if we can expand on that, that's going to be very valuable. The experimental effort, we need to work on. I think we need to really work on, but I can tell you that we also need a lot of patience on that. I've had such experiences with other countries. It has taken a better part of 10 years to develop a full-fledged community. So we are not going to be in a hurry. We shouldn't be in a hurry. But, and the reason why I'm telling you is that there are groups which are very strong already in the high energy side. And that is a very excellent thing. So we need to make communication with them and try to get some of those to get involved with the detector components, because the nuclear physics and high energy physics, we use the same detector technologies these days. So there is really no difference. As soon as you go from large group building a detector in high energy, we should approach them and see what we can do. And for that, these kind of meetings to expand science connections, I see it in the high energy, what they are interested in is also important. And that means that we need to have a lot more communication. And I think that I promise you now, knowing what is going on in this country now and in the neighboring countries, we will try our best to expand the communication. And it has to be two-way. I completely agree with what the discussion we had. It's a two-way communication. And I think we have resources that we can start with. So that brings me to the end of that part of the discussion. And again, go out of that and say, we have these two components. The IANN-QCD is a NSF-funded initiative that is really meant to enhance communication on the American continent. And we want to use it at maximum as possible. There were lots of opportunities available for student visits or senior scientist visits, both ways. Yeah. And so if you have ideas, if you have questions, please, some of the seniors know a lot more about it now, but just talk to us. Students, postdocs, send a message, and we'll try our best to do that. When we run out of that money, we don't have infinite money in that, but we have not used it because of the pandemic. So when we run out of the money, that is a good sign. So when we run out of money, it's a good sign. We can go back. That's a sign of success as far as NSF is concerned. So they are aware of this. We're going to meet with them in July again, mid-July, to tell them all the successes that we've had. And this would be one of the success stories I think we'll be launching on. So I think we should not be worried if you get a response from me, say, hey, we already funded 5 people, I can't do it. Don't get discouraged, because there's always the next year. So don't worry about that. So don't get discouraged. Keep on these things. And then I think the last thing I want to say, just on behalf of everyone, what we saw here in terms of success of this meeting couldn't have been possible with the resources of this center here. You have a fantastic institution with the kind of thing, the hall, the neighborhood, and the weather. I don't know how you manage that so it couldn't have been possible. I want to thank the people sitting behind there. They did a fantastic job of running this meeting, essentially flawlessly. And very last but not the least, I think the local organizing committee needs a huge applause from us, led by Bruno and his local colleagues. So let's give them, it really could not have been possible without them. Thank you very much for doing everything that you did. I think this is, I hope this is just a beginning for our communication. So, and this is exactly what Poetic was meant to be, that we go to places and we expand. So thank you very much. So thank you.
Thank you, everybody. So again, thank you to all the speakers. And I think I agree that the quality of the talks, and I was a little bit concerned, but it turned out more like a workshop, and actually I think it turned out for the best, because we had a lot of discussions. I liked a lot this discussion we had on Thursday afternoon about possibilities in Latin America. So I enjoyed myself a lot, and I think it wasn't neither stressful nor boring nor nothing. It was just the right amount. Thank you again. Welcome all these people here for helping us. And I have to say also thank you to Brookhaven and JabLab for the generous support that helped actually here financing this workshop. The Principia Institute, which started just recently hosting these workshops. Nathan was here recently. He was here before the last talk. The director of the ICTP SAFRA, Nathan Berkowitz. And I told him, by the way, that we are gonna, because he's also in the Sao Paulo funding agency, right? He's in the council there and one of the directors, that we would approach him and other people that we can maybe have an agreement, EIC, presents on. So something more political, having a little event where you could come or Elke could come and present. And they're actually very interested in having agreements with institutions. It could be with DOE, it could be with centers in France, and I don't see why it couldn't be with EIC, for instance. So we should do this also. And thank you anyway for coming. I know for many people it's a long trip. I know because I do this too often, but I hope it was worth it. And we think we have a little presentation to finish this, right? Which Alene created, and I think it's a cute thing. We were asked at the very end. I mean, I think we're a little bit decimated, probably like a third or 50% of the population left. But we were asked by the staff to all stand here at the end, and they'll take a group picture of us. All right. So thank you very much, and see you at the next Poetic, or better even before, right? Thank you.